My name is Oren, and I'm going to present our architecture for accelerating graph operations through relational joins. So recently, a new family of join algorithms revolutionized the database community. These algorithms enable efficient execution of graph pattern matching queries using relational joins. Specifically, TricJax, a new join algorithm we published in EWPT 17, is highly amenable to hardware acceleration and can utilize the available memory for speedup. Here we present the TrieJax architecture based on the TricJax algorithm, which is an order of magnitude better than state-of-the-art accelerators on these types of queries. And compared to TricJax, it is 20 times faster and 110 times more energy efficient. Let's start with a simple example of what is a join query. Here we have three tables: user posts, post likes, and users followers. We can combine these three tables using a Dist join query that returns the information about posts liked by users with followers. The traditional join algorithms will use a mechanism called pairwise join, which means that at each step they are going to join exactly two tables and create an intermediate result. But the problem is that they may generate huge intermediate results, that many of them are unnecessary. Now let's see how we can translate a join to a graph pattern matching query. So given the tables and query from before, we can visualize each row as a graph node. We will have an edge in the graph if two nodes match on a join variable. And in the case of our join query, we need to look for all the paths in the graph that are the size of 3. So for example, these paths. And there can be other join queries on this set of tables. So for example, looking for all the cycles of psi3 on this set of tables and so on. So TricJax, our join algorithm, utilizes another join algorithm called Leapfrog try join. So I'm going to explain the main ideas behind it. First, the tables are stored in trie structures. So each variable is a level in the trie, and each row is a root to leaf path. Now, we're going to determine a join order on the join variable. So first X, then Y, and finally Z, and add pointers to each level in the trie. Now, based on the join order of the join variables, we're going to start looking for matches for each join variable. So we start with X. The first match is 1. Now we're going to move to the next join variable Y, but before that, we're going to focus on the children of the match in the trie. So the children are 1 and 2. So now let's move to Y. We find the first match, which is also 1. And then again, we're going to focus on the children of the match in the trie. So children are 2 and 3. And now we're going to look for a match for the next join variable, Z. And once we have a match for all the join variable, we print out the result and continue in a backtracking manner until we can't find any more results on the first join variable. A very important property of the last algorithm is that no memory is used other than the tries. But the problem is that recurrent joins are recomputed, so we're going to rescan the memory again and again. To illustrate how big is the problem, we're going to use the mass count disparity plots. So let's focus on the left graph. The blue line shows the overall trie elements sorted by the number of accesses to those elements. So for example, this point is the number of nodes accessed less than 10 times. The green line shows the overall accesses. So if we focus on the right side, we can see that 20% of the nodes between 80 and 100 are in charge of 80% of the accesses. And if we look at the right graph of the 5-cycle query, you can see that 5% of the try nodes are in charge of 80% of the accesses. So there's a substantial opportunity for caching. Now let's move to CTJ. CTJ utilizes LFTJ, but given a generic join query, it detects valid caching opportunities. And in our research, it led to a 14 times speed up. Now let's see how we can utilize the cache. So we have the same simple join query from before, but now we're going to have a cache from the Y join variable to the Z join variable. And we're going to run LFTJ as before. And when we get a result, we're going to store the relevant entries in the cache. And at some point, we're going to reach a Y value that we've already seen. And then we can just extract the result from the cache instead of recomputing the join. So why is CTJ a good fit for hardware? We know that it has low and flexible memory footprint and fewer memory accesses. This graph shows the number of intermediate results of CTJ compared to a pairwise join used in another database accelerator. And it shows that it reduces the number of intermediate results by 15 times to 1 million times. Now let's talk about the TricJax Accelerator. We focus on complex join queries, and the design is a derivative of the CTJ pipeline. It is integrated as an on-chip accelerator to avoid coherence and data transfer, and we aim for a size of a small core. We want highly concurrent execution to leverage the inherent parallelism of the algorithm, and we aim for efficient memory accesses, so the CTJ caches will be stored in a local sketchpad inside the TricJax core. This way, no intermediate results will overflow to memory. Finally, the final results will be streamed directly to the main memory to not thrash the caches. This is the high-level architecture of the TricJax system. Here you can see the TricJax core, and the caches will store the input relations. We're going to stream the output directly to memory, but we're going to check the last level directory for cache coherence. If we focus on the TricJax core, we can see the components. First, we have Cupid, which is in charge on the try join over all join variables. It uses Matchmaker, which is in charge on the joins on one join variable. And it uses a component called list upper bound, which implements parallel binary searches. And finally, we have the midwife, which is in charge on extracting children of a node in the try. Now let's look at the operational flow. We first load a compiled query, and then the Cupid will start the join on the first join variable. So it's going to send all the arrays of the first join variable to Matchmaker. Matchmaker will use the list upper bound to find the first match of the first join variable, and they are going to iterate until we find a match. Once a match is found, it's going to be sent back to Cupid, and Cupid is going to move to the next join variable. So it first needs to focus on the children of the first match in the try. And for that, it uses the midwife. Once we find a match for all the join variables, we stream the result to memory. For multithreading, we have two schemes. The first is static multithreading, where we split the search space before the run on the first join variable. This scheme is used by a current GPU implementation of Leapfrog try join. The problem is that it creates an unbalanced workload. So for example, this thread 1 does all the work in this case. We used another multi-threading scheme called dynamic multi-threading, where we split the search space on a match. One thread goes down and another goes right. This creates a balanced execution, but a slow warm-up, which is solved by the static multi-threading. As for the CTJ caching in TrieJax, we have two flows. The right flow is in charge of LFTJ, and the left flow is in charge on CTJ, and it contains a local sketchpad called the PJR cache, partial join results cache. So we said that we have two parallel flows, and the CTJ flow will work as follows. Every time we have a match, we're going to search the PJR cache for the next variable matches. If a match is found, we're going to extract the results from the cache and avoid the recurrent join and the rescanning of the memory. If we don't find a match, we continue with LFTJ. Of course, every time we combine caching and multi-threading, we have issues. And in this case, we had several issues. The first is read-write, where a reader tries to read an incomplete entry. So we added an insertion buffer for partial entries. The second problem was write-write, where two threads reach the same partial join and try to update the same entry. So what happened is that entries could have duplicated values. Our solution saved the allocator's prefix and used it to validate that only the allocator can update the entry. And the last problem is, how do we know when an entry is done? We know that we can have multiple threads working on the same entry. So to solve that problem, we added a bookkeeping to the entry to detect when the last thread is done. And when it's done, we move the entry to the PJR cache. For the TrieJax evaluation, we implemented the components in PyRTL and then compiled it to Verilog. We synthesized and used place and route using the OpenCell 45 nanometer library. And we got 2.38 gigahertz frequency. For DRAM simulation, we use Ramulator for performance and DRAM power for energy. And for SRAM, we use Cacti 6.5. The total estimated size of our core is 5.3 millimeters square. This is the TrieJax evaluation details. I'm not going to focus on that. So first, we need to determine how many threads we're going to use in our system. And this graph shows that the TrieJax core performance peaks at 32 threads. But actually, the system energy efficiency stays about the same. And we're going to explain why in a few slides. So now let's talk about the performance. We compared TrieJax to the state-of-the-art database accelerators, Q100 and Graphicinado, and state-of-the-art worst-case join systems, empty-headed and CTJ. And this graph shows that we are 6 times faster on average than the second best, which is Graphicinado, and 20 times faster on average than CTJ. As for the energy, you can see here the energy distribution in the system. And you can see that the energy consumption overall is dominated by the DRAM. And this is why the TrieJax multithreading has a very small effect on energy. And it's because the TrieJax core is only a fraction of the overall energy. For energy efficiency, this graph shows that we are 15 times better on average than the second best, which is Graphicinado, and 110 times better on average than CTJ. Now let's see what is the effect of the architectural solutions. Specifically, what happens if we compare TrieJax to a variation that just uses the standard memory caches. meaning that we don't bypass the memory caches for the final results or use the local scratchpad. So compared to this variation, TrieJax speedup is 75% and up to 3.5 times. We also tested different other variations, and they show that the PGR cache is mostly beneficial for cycle queries, and the cache bypass is mostly beneficial for path queries. As for conclusions, we've seen that new class of algorithms enable efficient execution of graph queries using relational joins. Some of these are highly amenable for hardware acceleration, specifically CTJ. And here we designed the TrieJax architecture based on the CTJ algorithm, which is an order of magnitude better than state-of-the-art accelerators, specifically 7 to 60 times speedup and 15 to 110 times energy efficiency on average. And compared to CTJ, it's 20 times faster and 110 times more energy efficient. That's it. Thanks.